Greetings all. Thanks for showing up face to face, Cheyenne. And Martin. I also feel like I'm teaching nobody unless there's at least a few people that show up face to face. Thanks, Eve. Cool. Well, the good news is, my friends, that we really have today and Thursday. We're not meeting tomorrow, but we have today and Thursday really just to kind of play around with what graphs look like, and this makes just a lot more sense. It's the derivative taking isn't terrible. I'm going to teach you some algebra today, some cool algebra tricks. But mostly we just want to be able to like figure out what graphs look like. And again, this is a bit of an archaic skill, just because of the fact that, we have graphing calculators now, but you can imagine somebody trying to play around with some complicated graph, scratching on the ground with a stick and so forth. And, they didn't even have a calculator to plug things in. And so I think an argument can be made, you future math teachers, an argument can be made that what I'm going to show you the next couple of days is kind of obsolete. Like, can't we just get out Desmos and get a graph of something and let's move on? And there's an argument for that. But in a sense, I want to show you how to graph something ultimately. Really, the first 4 chapters of chapter 4, first 4 sections of chapter 4 are really just about how to analytically graph something. In other words, figure out what the graph looks like based on what the tools calculus gives us. And so I want to show you something about that right now. So this is one of the cubed equations, and I stole this Desmos actually from, I want to say Caesar, who it doesn't look like is here yet. But a few of you actually solved the project 3, not just for the one particular graph, but for all graphs. And so this is kind of cool. I stole it. But you already know some of this. And so let's stare at this for a second. Like, down here, the slope is really steep, and I drew the blue line in so you could see it. And of course, notice the slope is getting smaller and smaller and smaller and smaller until it actually hits 0 right there. And so we talked on 4.1 about how to find that. That's kind of cool. If we take the derivative and set it equal to 0, we'd be able to find that. And then it just keeps getting smaller and smaller. But notice right in here somewhere, it actually starts getting bigger and bigger and bigger. And so all through here, the slope is negative. So we say it's decreasing. If this was a stock, then we say it's decreasing all through here. And then it hits 0 again, and then it actually starts increasing again. But I want you to notice there's something the second derivative tells us today. And that's kind of what I want to get into about this picture. What does the second derivative tell us? So what I'd like you to think about is, would you agree all through here, the slope is getting smaller and smaller and smaller until it hits 0, but it actually just keeps getting smaller. So let's stare at that slope for just a second. So let me bring it out here where you can look at it. So now you can actually see the numerical value for that slope. So the slope is positive. It finally works its way to 0, which, if this is the value of your stock or something, is kind of depressing. And now it's actually negative and it's going down. But my question is, how far does it go down? So let's think of this as, well, this is a rate of change. And so let's think of this as like a 15% loss. So your stock is losing 15%. It doesn't tell you the value of the stock. It tells you how much it's actually losing. It's losing 15%. And now it's down to, it's losing 20%. It's just getting worse and worse. Like, you're totally depressed right now, right? Not only is your stock negative, but it's actually getting worse. So now it's down to negative 3.5, 3.6, 4.0, 4.2. Like, how bad is this going to get? Like, how small is this actually going to get? What do you think? 0.46, 0.47, 0.48. Like, how bad is this going to get? 4.9. Looks like it's actually getting right around 50%. It's 0.499. Like that's the worst it gets. Like right in there is the sort of the biggest negative number you would actually get. And notice from then on, it actually starts to get better. Notice it's climbing away. And by the way, I didn't stop there exactly, but it actually gets right on. If I make it right to 8, I'm going to try to just land on 8 exactly. Perfect. I made it. That's the actual worst spot. When you're right on 8, when you're right on X is 8, that's the worst rate of growth you ever had. That's the lowest rate of growth you ever had. That's the, or you could say the biggest negative number you ever got. Does that make sense? That's kind of an interesting place to be. Also, I'd like you to notice something. In a sense, this is an interesting place to divide the graph, because would you agree over here, the entire graph kind of looks like a downward parabola? But then on the other side of that, it's like an upward parabola. That's actually the division between concave down and concave up. But notice from here, see, that's the worst, negative 0.5. Now it actually starts to go back up again. Now the slope is, it's still negative, but notice it's getting less negative. You should start being like, hey, this is getting better. Things are actually getting better now. Yeah, my slope is still negative, but notice it's actually increasing. The rate of change of it is actually increasing every day. This is what a second derivative tells you. It's the change of the change. And then right here, you get back to a slope of 0, but notice now it's actually positive. And so it's just getting better and better and better. What I'd like you to notice is watch what the second derivative is. I'm going to bring the second derivative out now so that you can actually see it behaving as well. Second derivative. And actually, maybe for a second, I'll just put away the first derivative so it isn't distracting. This is the change of the change. This is not the slope now. It's how is the slope changing? What does it mean that the slope is changing negatively? Notice it says the second derivative out there is negative. What does that tell us? That the second derivative is negative.
Well, the graph is curving down.
Yeah, it's actually telling you that the graph is curving down. It's actually telling you that the slope is going to get smaller. Does it make sense? This is telling your slope is going to change negatively, which means your slope is going to get smaller. And notice you can tell from the green graph, yeah, the slope is going to get smaller as you move along. The slope is leveling out. And so that's going to make it, if you will, concave down. So the slope is negative. The change is the slope is negative, negative, negative. And notice if you get right to the top of that up there, it isn't 0. It's telling you it's still negative. It's still, you're getting worse and worse and worse. Your slope is getting smaller and smaller and smaller. In other words, the second derivative went right over that maximum up there with kind of without ever any way to even notice it happened. Notice nothing weird happens right there. But notice that number is getting smaller and smaller and smaller, which basically means there's reason for hope, because now it's only a 12% drop. Like, yes, you're still losing. Your slope is getting steeper negatively, but it's actually getting steeper at a slower rate. What happens right at that point? Remember where it was 0.5? What happens right there? Notice your second derivative is equal to 0 at x equals 8. When x is 8, you actually have a second derivative that's equal to 0. That's how you find that point. That's how you find that other cool point, the transition from concave down to concave up. And so in a sense, if this is a business, like this is a really good day, because it basically means now things are going to start looking up. Now you still have a negative slope. Your business or your stock is still losing money right here. But from here on, what you're going to notice is the slope is actually, well, the change of the slope is actually positive. Does it make sense? That's good news. The slope is negative, but fortunately it's positive. The change of that slope is positive, which means the slope is now getting steeper and steeper and steeper. Do you see the slope getting steeper and steeper and steeper? Whereas over here, what was the slope doing? It was getting flatter and flatter and flatter. Does it make sense no matter where you are over here when it's concave down? The change of the slope is always a negative number, because it means as time goes by, it's getting worse and worse and worse. Whereas once you get on the other side of this, notice you always have a positive change of slope. Again, it's not telling you the slope. We already have a way to know what the slope is. This is saying the change of slope. And so that change is getting bigger and bigger and bigger. Let's look at them together really quick. So if you're over here, you have a positive slope, and that's good. This is your business. But unfortunately, the trend is downward. See how the second derivative is negative, and so it's like you're positive. That's good, but unfortunately, your progress is beginning to level out. It's like going to the gym. It's like you're getting stronger every day, but unfortunately, it's starting to level out to where it's kind of hinting that you're going to reach a plateau here. So the fact that the slope is positive is good, but the change of the slope is negative, that's not so good. It's telling us that this graph is leveling out here. When I get up to that peak right there, of course, I get a slope of 0, but unfortunately, this second derivative is telling you, unfortunately, the trend is still downward. Like this is just going to get worse. The trend is going to keep getting worse.
I feel like this would be super helpful in like the business world for analytics, like reviewing, like, trying to sustain a business loan. Like they're like, cool, we'd like to see like how your profits are, but like, let's see the real picture. Like, are your profits starting to divvy off?
That's right.
Yeah.
So it's not just what's happening today. Ooh, things are good, they're growing. But the second derivative tells you, yes, they are growing, but unfortunately, it's beginning to level off now. And so you're exactly right. And as I've mentioned before in this class, there's a class called business calculus that is not as heavy on learning how to take derivatives, but it's more about analyzing graphs like this so that you can kind of predict the future. Notice over here, both of them are positive. Not only is the slope positive, but the second derivative is positive. What does that tell you about your business if both the slope is positive and the second derivative is positive?
It's going up and it's growing faster and faster.
Yeah, it's like today is good because you have a positive slope, and tomorrow is even going to be better. That's what the second derivative being positive tells you. It tells us as I move to the right, my slope right now is 1.38, but as I move to the right, it's going to get even bigger. This is like exponential growth. Today is good, tomorrow's even better, and the day after that is even getting better. I mean, this is just good, good. What is this saying over here? Still a positive slope, but unfortunately tomorrow's getting a little worse. You see what I'm saying? Today is good. Like there's a place over here that has the exact same slope as this one does, except for over here, the trend is downward. So that's why concave down and concave up are kind of important. Plus, just in terms of the, just making a graph at all, this transition point right here is really kind of cool to know. It's like, that's the transition right there from concave down to concave up. And so it helps you kind of understand a transition in the graph. And so that's what we're going to talk about today is that second derivative. And so let me write some of that stuff down a little more formally and see if you can get it to go into your brain.
Makes me think of like the stock market too. Like you could use these trends to know exactly when the right time to sell a stock would be.
That's exactly right, Jesse. This is very much a business model and like a stock market model. And I think it helps you get your mind around it to see that. The problem with the stock market is finding an equation that you can count on, not analyzing the equation, but finding an equation that you can actually count on. That's kind of a matter of guesswork in that world.
It seems like candlesticks are really effective though.
What do you mean?
Candlestick graphs in stocks, from what I've seen, is like they're able to show like the substantiation of stock between figures. So like how much value is that stock growing at that moment versus how long it'll stay there.
Right. That's right. How it's growing right now, but how long is it going to continue to grow before it's time to sell? That's exactly right. And that's exactly what this is adding. So your book calls this like what derivatives tell us about graphs or something like that, but I'm going to sort of title it something a little bit more more meaningful. That point where there's a transition between concave down to concave up is called an inflection point. And so really that's what we're looking at today. So let me just draw a rough graph. Let me just kind of formalize what we just did a second ago. So let's just remind ourselves of some things we already know. Would you agree from here to here and from here to here that this graph is increasing, like things are good through there, which again for us means that our first derivative is actually a positive number, because isn't that what increasing means? It's like a positive slope. And maybe I'll write the word positive just to make sure that's really clear. Whereas if I go to this section, is it enough of a different color? That's actually decreasing, which is really code for us in terms of analytically looking at a graph. That's where you're going to get a slope that's actually negative. So that's what you already know. There's positives and negative slopes, and that tells you in business, hey, you got an upturn. Things are good right now. Up, things are bad right now. Up, things are good right now. But this transition idea that really a few of you have been mentioning, Cody just talked about, it's like the trend of it and so forth. Well, that's where these second things come in. And of course, the transition, let me say this right now, the transition between, well, the red and the green are these maximums and minimums. And so those are where the derivative is not positive or negative. It's where the derivative is actually zero. Not x is equal to zero, but the derivative is equal to zero. The slope is equal to zero. So that's a transition between increasing and decreasing. You already know that. But today what we're talking about is kind of like this point here, which is there's a transition between, and this is what's called an inflection point. I guess I'll rewrite it. You should have never heard of this word before. If you have, you can't really understand what an inflection point is without calculus. So you probably have never heard of it before. But it's really the transition between concave up and concave down. So let me kind of add that to the graph. This part right here is concave down, which is where the second derivative is itself negative. In other words, it's a bad trend. You're doing good, but it's leveling off and leveling off. So concave down is where the second derivative is negative, whereas over here, where it's concave up, that's where the second derivative is actually positive. And again, the inflection point is the transition between those two. Like that's where the change happens. And so, of course, the inflection point then would be where the second derivative, and this is what we saw just a minute ago, is actually equal to zero. That's where the transition happens. And so these two things, not just the derivative set equal to zero, which tells us what your book called critical points, but it really just means slopes are zero right there. Those are big moments in your stock value, but inflection points tells you when there's a change in the air, there's a change in a trend. So let's see if we can, let's look at a practical example now and see if we can learn something about it. I wish I'd started this on graph paper. I wonder if I can change to graph paper in the middle of this. Apparently I can. So let's look at this example. And this is not a great example to start with because it's pretty confusing. Like there's some surprises to this particular graph. X to the 2/3, but then it's multiplied by x squared plus 3x plus 2. Now, again, what we want to do is try to analyze this thing analytically. We want to try to use calculus to get a feel for what this graph looks like. And this is what I mean when I said, isn't this skill a little obsolete? Like, can I just get in Desmos and 3 seconds later, I have the graph. Yeah, absolutely you can. And I'm sort of tempted to do that, like give you the graph right now, but let's just kind of play around with what I just showed you on the top first and just kind of try to analyze this graph, well, in the way a caveman would have, that didn't have any of these tools. But one thing I want to say is, despite the fact that, this is like, well, let's do calculus to do something we don't need calculus for anymore. There's an argument for that. But I'll show you on this graph how these skills in calculus that I just showed you will make you aware of something in that graph that you wouldn't have otherwise noticed, I guess. So let me show you what I mean. Well, first let's get the stuff we already know, which is, what about the derivative? What does the derivative tell us about the graph? And that's why your book titled it this. What do derivatives tell us about graphs? Well, they tell us where maximums and minimums are when we set that derivative equal to 0. And so let's go do that. And then I'm going to show you, so this is not new, like you should already know how to do this, but here I'm going to show you some cool algebra tricks that are going to make your life a little bit easier. Because remember, we're not just taking a derivative and saying we're done with it in chapter 4. We're saying what good are derivatives? Let's use them for something. So, okay, if you take the derivative of this, you should be thinking, well, what are you thinking when you look at that in terms of rules? How do you take derivatives? Like, what rule am I going to be using here based on that equation?
Product rule. And power.
Good. Product rule is the governing one, and then the things that I'm multiplying are powers, and so it's like, yeah, product rule and power rule. So product rule says derivative of x to the 2/3 is bring the 2/3 down front, and now take 1 away from that 2/3, which is not good. That makes it negative 1/3, times the junk left alone, plus the x to the 2/3 left alone, but then times the derivative of the parabola, if you will. The parabola derivative would be 2x plus 3. Are we okay with that? Like, there's the derivative. And as far as calculus in chapter 3 goes, well, you're done. There's the derivative. Good for you. Remember, in this section, we're interested in not just what is the derivative, but we're figuring out when f prime of x is equal to 0, that gives us maximums and minimums, right? Or again, what your book called critical points. I hate adding that language to it. Why not just say setting it equal to 0 gives us maximums and minimums? So we got to set this equal to 0 and solve for x. And so this is a pretty daunting equation to set equal to 0 and solve. And also, we're not even done because we still have to take a second derivative of this. And so the idea of, can you algebraically clean this mess up a little bit is really kind of cool and kind of helpful. Let me show you a trick here that's kind of neat. You should not need me to set this equal to 0 and solve it. But let me just show you something we can do to it that'll be really nice. So I'm going to copy this graph. And now I'm going to do something that you probably would not expect, which is I'm going to think of this like a fraction over 1. And I'm going to multiply this thing times x, top and bottom, times x to the, let me scoot this over a little bit, times x to the 1/3, top and bottom. Now, why did I pick x to the 1/3?
You eliminate one of the x's and keep one on the right side.
Yeah, it's going to make this mess right here not so messy. The other thing I'm looking at here is, don't forget this plus sign, because what this means is I have to multiply x to the 1/3 times this and times that. Isn't that what distributive law says? And while I'm at it, so one thing I don't like is I don't like x to weird powers. Like if I'm gonna have to solve this or like do algebra to it, do math to it, I really don't like the fact that that's x to the 1/3, x to the 2/3. I want it to be things like x to the 1 or x to the 2 or x to the 0. Nice things. And the other thing I don't like is fractions, and the fact that this says 2 divided by 3. Couldn't I also multiply it by 3 and get rid of that fraction? Like, this is just cool pain-saving stuff. And so let's see what happens if I did that. So when I multiplied, go ahead, Eve.
Can't you move your 3x to the 1/3 down because it's a negative 1/3. So can't you just move it to the bottom of the fraction without multiplying it in?
So what Eve is saying is, can I just get rid of it? And I want you all to consider this because it's a good question. Can I just get rid of this and move it down here as x to the 1/3? The answer is no. Why not?
It's not shared with the other.
Because they'll
terms.
split the graph in half.
Yeah,
Or the-
split it in half because there's a plus sign. If that plus sign wasn't there, we could have done that. But with that plus sign, that kind of screws that all up. And so in a sense, I'm avoiding potential mistakes by doing algebra to it. And so, yeah, it's kind of like screwing up the distributive law effectively, Eve, if you do that. And so if you separate it into two totally different fractions, you could get away with that. In other words, if I didn't have a giant division sign, but I kind of chopped it in half right here and had two separate fractions, I could do that. And so just watch how much this cleans it up. And again, there's lots of things you could do here. I'm not saying this is what to do. There's all kinds of things you could do to this, but this is just one that's really good. And so let's see what happens to this. Well, when I multiply this 3 times this 3, that will cancel out. What happens when I multiply x to the 1/3 times x to the negative 1/3? What happens to that?
It becomes 0.
Wow.
It becomes x to the 0, which I'll go ahead and write in here, but then I'll say that's 1. And then for now, there's still an x squared plus 3x plus 2. But you notice how much easier? That's like 2 times x squared plus 3x plus 2. That's really cool. What happens when I multiply the next one? What's x to the 1/3 times x to the 2/3?
It becomes a whole number.
Becomes, because you add exponents, it becomes x to the 1. So I have a 3 because it didn't cancel this time. And then it's times x to the 1 and then times 2x plus 3. Now the denominator got ugly. But let's continue from there and see where this goes. And again, please stop me and ask questions like, wait a second. It gives us time.
Could you go over the reasoning again, why you chose 3x 1/3 over 3x? I know it's equal to 1, but can you go over the reasoning why you chose that fraction exactly again? One more time, please.
Yes. So the reason I did it is because oh, that's not good. I've got to get the whole thing over there. The reason I did that is because of what happens to these two terms right here. They used to be x to the negative 1/3 and x to the 2/3. And I noticed if I chose x to the positive 1/3 outside, then that would turn the first one into x to the 0, which is great because that's just 1 and it goes away. And then it just turns this one into an x to the 1. And so my exponents became x to the 0 and x to the 1. Like I like those exponents a lot better than I like negative 1/3 and positive 2/3. Because remember, I have to do something to this. Think about that. Well, since this one actually becomes 1, then what I have on the top is really 2 times x squared and 2 times 3x and 2 times 2. And then I have 3x times 2x, which is 6x squared, and then 3x times 3, which is 9x. Notice again, the bottom is ugly, but let's think about what we're doing here in a second. And so now I'm actually down to where I can say the derivative. I can rewrite it now as 8x squared, and then 6x and 9x is 15x, and then there's a 4 all over 3x to the 1/3, or I could write cube root of x. Like this is much nicer. Much nicer than that green derivative. Why is it nicer? Well, because what am I doing to this derivative? I'm trying to set it equal to 0. I want to set this thing equal to 0, because isn't that how you find maximums and minimums, is when the slope is equal to 0? Now do you see the brilliance of this? Because if a fraction is equal to 0, which one of them is equal to 0, the top or the bottom? Or both?
Either of them, right?
The answer, only the top.
Only the
okay.
top.
So really this means now I can just figure out when is 8x squared plus 15x plus 4 is equal to 0. Because remember, I have to do something with the derivative this time. I don't just get to say in chapter 3, oh, I found the derivative, I'm done, stop. No, I actually got to do something with this. And so this is just easier to work with. The second thing is remember, I still have to take the second derivative of this thing. And so I'd like it to be as nice as possible. This is not the only way to do this, but this is awful nice, I guess is what I'm saying. The green equation that I had back here, if I set that equal to 0, this green equation, if I set that green equation equal to 0, that's awful messy. Now, can you still solve it? You bet you can. Because one of the first things that you might want to do is multiply both sides by x to the 1/3, or now you could add one of those to the other side. It's not that you can't do that. That's not a terrible idea. Please understand. I'm just saying I think this one is nicer. And so I hope you have the quadratic formula program in your calculator. So the quadratic formula then, I'm sticking this in my calculator really quick. And when I do that, I get that x is approximately negative 0.32, and x is also approximately negative 1.55. So what this tells me is, oh, there's two maximums and minimums. Now they could both be minimums, or one could be a minimum, one could be a maximum. I don't know, but there's two places where the slope is 0. And notice it's also cool that there's not 3, there's not 4, there is 2.
Can't we figure out which one's maximum and which one's minimum without the graph? Like based on, we know that negative 0.32 is higher up than negative 1.55, so it wouldn't make sense, if you know what I'm saying.
Yeah, let's take a look at that. So now, of course, I only have the x coordinates and I need the y coordinates too. So don't I have to go back to the original equation and take 0.32 and put it back into it? Remember that original equation clear back here. So I'm going to put 0.3. Do this on your calculator really quick. Again, we're trying to do this analytically. But if you put negative 0.32 into that expression right there, then you'll get the y coordinate that goes with it. So when I do that, if I don't screw this up, I get about 0.53, positive 0.53. And when I put negative 1.55 in, I get about negative 0.33. So now I'm really someplace cool in the sense that I can say, if I haven't blown it, you please tell me if I blew it. I can say that I have maximums and minimums at negative 0.32, 0.53, and the other one is negative 1.55, negative 0.33. Like this is a big takeaway. Like that was a lot of work. And really, that's what I wanted. That's what I wanted all this time. And so let's get that on a graph. Let's stare at it and kind of consider what Eve just said a second ago. And notice those are pretty small numbers. And so I'm not going to use the boxes as being worth 1. I'm actually going to try to use the boxes as being worth 4. Like each box is worth a 4th. Does that make sense? So that I can make a better graph of these. And so let's graph those maximum minimum points. So negative 0.32, this is 0.25. So negative 0.32 would be about there. And then I go up 0.53. So I'd be about here somewhere. Would you agree with that? And then the other one is negative 1.55. There's negative 1.5. And then down 0.33. So it'd be like around here someplace. Maybe. Let me go in and take rid of those marks. But does that look right if I make those worth? And I'll write this in here. There's 1 and there's 2 and there's -1 and there's -2 and here's 1 and here's -1. Does that look right? So everybody understand what Eve said? Eve has said is, you know, one of these is below or above the other one. And by the way, Eve, you didn't know that until we found the y coordinate. Does that make sense? We didn't know one was higher or lower.
Yeah, I was talking after the y coordinate. I was just a little bit thinking.
So would you agree that what Eve said is probably true? Like, doesn't it kind of indicate it would look like that? Like to get from one to the other, doesn't the top one often want to be the maximum and the bottom one wants to be the minimum? So, you know, that's a good conjecture. We can't know that for sure. Could it be the opposite? Could it be like this? So part of me wants to say no, because in order to connect, wouldn't it have to do this to connect? And why can't it do that?
Gives you more mins and maximum.
Yeah. What I said before, the fact that there's a minimum and a maximum, there's 2 of them, not 4, means it can't do what I just showed. Does that make sense? The algebra says no, it can't do that.
And doesn't the fact that it's just a parabola affect it?
Yeah, and notice it's kind of just a parabola, but it's also being multiplied by x to the 2/3. And so remember, I could have taken this derivative by distributing. I could have actually distributed this in if I wanted to and wrote this totally different. So ultimately, it really isn't a parabola. And maybe I should have. Maybe I should have multiplied that x to the 2/3 in. Maybe that'd make my life easier. Maybe that'd have made the algebra easier. Maybe that'd made the calculus easier. Those are all good questions.
Could it be one of those weird graphs that has a parabola up top and then a parabola down low?
Yeah, like there actually is no reason that this couldn't look like this. And it's like 2 separate graphs. And so that's not impossible. And that's what's kind of cool about this. We're actually not sure. I mean, most likely it doesn't do that because that's a really unusual graph. But if it connects smoothly, and this is why your calculus book says things like it's continuous graph. Notice this graph is not continuous. It's broken into 2 parts. And so and this is why the second derivative is really cool. Does it make sense that the graph I have right now, at the top point, it's concave up and the other one, it's concave down. Whereas we're saying, you know, maybe we're saying, I don't know if it's that way. I think it's more normal. It's probably more like that. I mean, don't you sort of expect it's probably more like the blue graph? In which case, you know, oh, okay, the concavity just changed. This is why concavity is kind of cool and why a second derivative tells us something neat. And so we're really not sure right now. Those are helpful. Those points are helpful, but we analytically don't really know for sure what this looks like yet. And the second derivative is going to tell us this. And so let's see if we can go figure out the second derivative now. Let me make those nice and big. I'm going to draw over the top of them later on. So now let's go figure out the second derivative, f double prime of x. Because we just learned a while ago that that's actually kind of helpful. And again, here's where it's kind of important what you do with the derivative, because I have to not just take this derivative, I have to set it equal to 0 and solve. And then secondly, I have to take its derivative again. And so I want this derivative, this first derivative, to be as nice as I can possibly get it before I have to take its second derivative. Again, I'm just going to take the derivative in the form it's in because that's good practice for us. Notice it's quotient rule now. And so I'm going to do the quotient rule just because I can. I mean, that's kind of the way that you should think about this. Maybe I could make my life easier, but it's like, well, I can take the derivative right now. So quotient rule, good reminder for us. Quotient rule. So quotient rule says the second derivative, the derivative of the first derivative, would be derivative of the top, which is 16x plus 15, times the bottom left alone, just putting this in English, minus the top left alone, times the derivative of the bottom. What's the derivative of 3x to the 1/3? Well, the 1/3 comes down front. 1/3 times 3, well, that's nice. It's actually 1. So the coefficient's just 1. And then the x value, I have to reduce the exponent by 1. 1/3 minus 1 is -2/3. So I'm not so happy about that. And then quotient rule says you got to go on now square the bottom. And so 3 squared is 9, and x to the 1/3 squared, x to the 1/3 times x to the 1/3, you add the exponents, it'd be x to the 2/3. So again, I'm done. There's my second derivative. But remember, I've got to set this equal to 0. What we said before back here was that inflection point can be found where the second derivative is equal to 0. So I've got to set this equal to 0 and solve it too. And that's going to help me tell what's going on. It's going to help me tell what's going on with this graph. And so I need to use this. And so I'd like to clean it up a little bit. Anybody have a good idea here based on what I said before? I'm really not happy with this 1/3 and this 2/3 up here. I sure wish those were 1s and 0s and 2s, like nice whole numbers, because to set this equal to 0 means I'm very concerned about what's on the top of this fraction. What could I multiply the top and the bottom of this by that would make my life wonderful? What'd you say, Val?
Multiply the top and bottom by x to the 2/3.
Yeah, I agree.
Vale says, and Cody agrees, that I should multiply top and bottom by x to the 2/3, they say. I'm just writing down what they said. Is that the best one? Is there another one? Are they right?
There's no other fractions on the top that we need to get rid of, so we don't need a coefficient like we did for the first derivative.
Yeah, there's no,
I think the best.
Right. There's no fractions up there, so that isn't, so they are right. Would 1/3 be good? Or negative 1/3? What about negative 1/3?
Yeah, that would also work.
Negative 1/3 is not terrible. If I multiplied negative 1/3 times this one, it would become x to the 0. I really like that one because now it's 1. But what happens if I multiply this one times x to the negative 1/3?
Times the -1.
It's x to the -1, and that's definitely better, but I really don't want any negative numbers. Does that make sense? So this is a good decision. What I want is 1s and 0s if I can get them. That's awesome. And that's exactly what happens here. And again, I'm staring at this negative sign right here, because if I don't see that, then I screw up the distributive law. This gets multiplied by this term and by that term. Now, a little side note, but wait, there's 2 things over here. Which one of these do I multiply by x to the 2/3? The parenthesis, the x to the 1/3, or both?
Just the x to the 1/3.
Yeah, because this is multiplication here, there's not a plus sign there. I don't have to do it to both of them. If I did it to both, I'd be screwing up the distributive law. So when I multiply a number, just like you do a number, if I said, what's 2 times 3 times 4, which one does the 2 get multiplied by? Pick one. Not both, pick one. Go 2 times 3, fine. And then 6 times 4 is 24. Or go 2 times 4 and get 8, and then 8 times 3 is 24, but not both, pick one. Well, which one are we going to pick? Well, we're going to pick the x to the 1/3 because that's the one we're trying to clean up. So this is what I mean about like the deep magic of distributive law. Like you got to really understand this stuff well to not blow it. So let's see, what do I get? Well, if I leave the 16x plus 15 alone and I multiply x to the 2/3 times x to the 1/3, I get x to the 1. And that's nice. I can live with that. What happens to this next one? I have 8x squared plus 15x plus 4. What happens when I multiply x to the 2/3 times x to the negative 2/3? Well, I add the exponents and I get x to the 0. And I'm very excited about that because that's actually just 1. And so that top just got easy to work with, just like the previous problem. Now, what happened to the bottom? Well, the bottom got terrible, but who cares about the bottom because I'm setting this thing equal to 0. So x to the 2/3 times x to the 2/3, I add exponents, so that's x to the 4/3, but I don't really care that that's so terrible. That's the idea here. And so then if I distribute this 3x into both of these terms so that I can proceed with this subtraction right here and collect all that junk together, just to give you time to process, that'd be 48x squared plus 45x minus, notice it's minus everything. If I didn't have that parenthesis, I might have screwed this up. It's minus 8x squared and minus 15x and minus 4 all over 9x to the 4/3. And so now I can say, I'm all very excited. We're all very excited now. My second derivative is actually equal to 48x squared minus x squared, which is 40x squared, 45x minus 15x, which is 30x. And then there's a minus 4, and that's all over something ugly, but I don't really care about it. So this is extremely good news. Now, what does this tell us? Well, let's go back to our graph. Remember, I said to you that if f double prime of x is negative, that means it's concave down. Remember that discussion? So let's use this derivative to kind of check that. Like, for instance, if I go back to this graph right here, and I'm wondering, I'm thinking logically to myself, I'm pretty sure right through here, this thing is concave down. Do you agree with that? I'm pretty sure that's true. Well, does it make sense I could plug in any x in here I wanted to see if I got a negative number? I could plug the actual coordinates of that point in. That was the x coordinate of that was negative 0.32, but I don't have to. So I'm going to pick this right here. I'm going to pick negative 0.5 and see what I get. This is just one of your options. So let's see what f double prime of negative 0.5 is. Well, that would mean if I went over here that I'd have 40 times negative 0.5 squared plus 30 times negative 0.5 minus 4 all over the top of 9x, which is x's. And the weird thing about this is I find myself wanting to not have to type this into my calculator manually, both because it's time consuming and also because I'm afraid I'm going to screw it up. In the interest of time, I'm just going to tell us this actually comes out negative. You do it on your calculator and double check that. If somebody actually figures it out what it is, like tell us what the number is, but that actually comes out negative, which means hence concave down. So this is pretty important. This is pretty cool that we can know this analytically. It means that that red drawing I made there is actually right. It is concave down. And if you went over to the other point, it's concave up. And so we actually, the thing that sort of feels like it would be true, that the graph has kind of looks something like that, turns out to be true. And calculus proves it, guarantees it, if you will. That's kind of cool.
I actually plugged it in and I got a positive number.
Did you put the 0.5s in?
Oh, I wrote the 0.5s as positive, not negative. Oops.
Thank you for trying it and being brave enough to just talk so we have time to process.
If you put the 0.5 in positive, wouldn't it still come out concave down?
Yeah, because it's a minus 4 or negative.
Yeah, see, the other part of this graph that the second derivative tells us something about is what happens now. Like, let's say I have basically this part of it right, but what happens next? Does this turn around and go up? Does it go down forever? Does it kind of level out? Like, you see what I'm saying? And that's what the second derivative being concave up or concave down tells us. And before we get ahead of ourselves, the thing that makes the most sense, even before we did what we just did, is probably to go find the inflection points. Because remember, inflection point tells us where there's a transition between concave up and concave down. So it makes the most sense, if you will, to kind of skip this and go down here and figure out when f double prime of x is equal to 0, because that's where the inflection points happen. Now, remember, we don't really care about what's going on the bottom. And so what we really need to do is just figure out when 40x squared plus 30x minus 4 is equal to 0. How many answers does that have, by the way, before we even start? How many answers is that going to have?
2, right?
2. It's a squared equation, has 2 answers. Now remember, you could have a negative under the square root sign and there's none. That's possible, meaning there's no inflection points. Would you agree if you had a parabola, there's no inflection points because it's concave up the whole time? No changes of concavity. But that doesn't happen here because I took the time to make up kind of a cool problem. And so, again, in the interest of time, let's, and you go slow and kind of confirm this, but if I stick 40x squared plus 30x minus 4 into the calculator and I solve for x, I get 2 answers to this. One of them is 0.12 for x. The other one is negative 0.87 for x. So there's a change of concavity at x is 0.12 and at x is negative 0.87. And then if I go put those back in, remember, to the original graph, like I need to find the y coordinates to go with those. If I find the y coordinates to go with those, I get 0.13 for the negative 0.87 and I get 0.58. So these are huge. This is huge. The zero slopes were huge, and now we can go back to the graph, and this is going to tell us a lot about our graph that we're trying to figure out. So just so that you can see him, I will copy all this junk and move it up there on the graph so that we can stick it on the graph and no, we're not screwing it up. So at negative 0.87, let's see, negative 0.87 would be, this is 0.75. Let's get it zoomed in here a little bit. This is 0.75. So 0.87 would be right there. And then it says you go up 0.13. So this is 0.25. So that means you go up about half that, about right there. Actually, doesn't that make sense? It would be about right there. Wouldn't that be an inflection point? Like that's actually agreeing with what we thought before. Over here, isn't it concave up? And then somewhere here, isn't it a transition from concave down? So that makes perfect sense that that'd be there.
Couldn't you use the mean theorem to solve that, to get that point?
The mean value theorem. The mean value theorem just guarantees, let's see, what does it guarantee? It just guarantees there's slopes between other slopes. It really just guarantees the presence of these things. It doesn't tell us what it is, I think, is the answer to this. Let me ask you a question. Why could this graph over on the left not do this and kind of level out? Why could, like, in other words, when this takes off to the left, how do we know what happens out there? Why can't it do that?
Wouldn't it eventually hit another slope at 0 if it kind of flattened out again?
Not necessarily. Not if it went up like this and just kind of leveled out like a square root graph does. It doesn't have to turn around and go back down again necessarily. But if it did do that, does it make sense there to have to be another inflection point over there? Because isn't this concave up? And then if it did that, isn't that concave down? There's no inflection point over there. So it does not do that. That's what I'm getting at. That's the reasoning, or why I gave you kind of a complicated graph. I know that over there, this actually must just continue to go up because there is no inflection point over there saying that there is a transition to concave down. That's what inflection points tell me.
This kind of looks like an x cubed graph. So if we were to distribute back in our original f of x equation, if we were to distribute that x is 2/3, would we get a cubed graph?
It's a good question. Now this is where it gets kind of interesting. So what happens on this side over here? Does it just go down forever? The answer is no, because there's another inflection point. Does that make sense? There's something over there telling us that it changes concavity. And so there's not just one inflection point, there's 2. There's not 3, there's 2. There's not 1, there's 2. Where's this other one then? Well, if I go over 0.12, which is about here, and then I go up 0.58, it's a hair above that then. So I got to change back to black. This one, the blue one was 0.55. And so this one's actually a hair above that. I'll exacerbate it a bit by putting it above it. So how in the world can there be an inflection point up there? Well, maybe it's, let's see, let's think about this a little bit. Maybe it does this. Maybe it turns around and does this. Why can't that be the case?
Because you have another critical point of 0.
Yeah. You have another 0 down there. You have another critical point. You have a 0 slope. It can't turn around there.
Isn't there an asymptote at 0 though? So it's actually coming from the top.
This is very confusing. Vale has a deeper thought, but I just want to give people the chance to soak on this a little bit. How in the world can there be a change of concavity right there and the graph not turn around? Like, I don't even understand how it could get to that other point. Do you understand what I mean? How can it even get there without turning around?
Is there a peak and it breaks?
So first of all, could it do this? Could it come up and actually level out flat for a second and then continue on like that? Does the 0 slope actually have to turn around? The answer is no. It actually could just be level and then continue on up again. It could do that. We haven't seen that before. That's a possibility. Let's see, would that make sense if that was the case? Again, I'm just trying to give you a chance to think about this. Concave down, concave down. No. Let's see, would it, because right in here, it started to be concave up. And so there'd have to be an inflection point right in here for it to graph like I graphed. And so maybe, is there some way that's like level, concave down, still concave down? This is very confusing. Like what? And this is not, I mentioned at the start of class, this is not a great one to start with because this is more complicated than I would really want you to be able to do. If the graph is not kind of smoothly connected, this is really confusing. So there's no more turnarounds, no more maximums and minimums, and somehow it's got to get over there and transition. Boy, that's really strange. What's going on?
Would it peak and like break?
What do you mean by
Is the
break?
graph broken?
Yeah, is there some kind of, like, remember the graph, this could be broken into 2 graphs. Remember that? It doesn't have to be continuous. It could be 2 separate graphs. So this is really challenging. Well,
What if it just went straight to it instead of being in a curve?
okay, that's a good idea. What if it just kind of went straight over to it? Well, notice.
I mean, from the 0 slope to the black dot.
Yeah, from the 0 slope to the black. Let's see. Let me see if I understand what you mean. So it definitely has to level out right there in order to have a 0 slope just for a second, if you will. And you're saying it kind of gets hustling right over there. Again, I'm thinking, does it curve up or curve down or go straight? I don't know. Like, how does it get over there? It can't curve down because that would mean there's another minimum. So it's definitely not that one. Can it curve up to get over there?
No, because that would add to the maximum.
Yeah, that might add a maximum. This is very confusing, isn't it? Let's see. Well, let me show you what it turns out to be, just in the interest of time, because I do want to do another problem. It turns out that this actually goes down like this. So don't forget your basic skills. Like if you look back at the original problem, like don't forget you can just find points that work. Would you agree that f of 0 is 0? Like 0, 0 is one of the points on this graph. Don't forget you can still find points. Again, this one is harder than I really want it to be, ultimately, like for a test or something, but it's cool for us to think about. 0, 0 is a point on this graph. What the heck? 0, 0 is a point on this graph? How could it be 0, 0? So that would make sense if it hit 0, 0 because it's concave down through there. But now how's it supposed to get to that black point without turning around? You see what I'm saying? And creating a minimum over there. Well, it turns out that it hits down there and takes off and comes back up here. It's pointed down there. And that's a place where the slope is actually undefined. And so something Vale said earlier is kind of true. The graph actually has an asymptote right there. I want you to think about something. And again, this is deeper than I want you to know, so don't freak out. But let's remember back here when we said, hey, when is this thing equal to 0? And we ignored the bottom. What's the slope at 0? What would the slope be at 0 according to this entire equation? If you put 0 in for x, what do you get?
4/0.
You get 4 on the top and 0 on the bottom. What is 4 divided by 0? It's not undefined in calculus, it's infinity. You get an infinite slope there. What? You get an infinite slope? Well, that's because of this. The graph is actually coming down at a point. Let me draw it even more extreme than I did before. It's actually coming down like this, and it's kind of getting infinitely steep right there, and then it takes off infinitely steep again. Again, not obvious. So does the graph then go like this? What does it mean that that black is an inflection point? Isn't that what I just drew concave down the whole time? Doesn't that black dot have to be a transition somehow?
Well, it could just level off like an x squared graph, couldn't it? Instead of having another critical point.
Yeah, and it doesn't have another critical point. It's very confusing. First of all, would you notice this is concave down the whole way, and then it's still concave down right there? That's all concave down. So what's that black point represent, that inflection point? It has to be concave up now. So what must it be doing? Well, it actually must be actually transitioning and going up this way, not that. You see what I'm saying? That would make it an inflection point. All I'm trying to show you overall is, do you see how, like for, I don't know, a caveman who didn't have a graphing calculator, it's like these points are really helpful. This is not as satisfying because it's got so much trickery to it, if you will. I want you to look at the real graph of this though, and I would like you to notice something about it. In the interest of time, there's the real graph, just cheating. Most of it looks like you would expect. And let me just make a copy of this so that I can stick it in the notes, because I want to draw on it a little bit.
Did you change your note paper to graph paper?
Yeah. Earlier on, I did that, which was really helpful for us to see what the heck is going on. So what do I mean? I mean, over here, it's concave up the whole time. Actually, let me highlight that. It's concave up the whole time until it hits that inflection point. Let me write that in there. This is an inflection point. So it's concave up. And then it switches, because that's what an inflection point tells me is, hey, something has changed. It's now not concave up, it's concave down. It actually continues to be concave down. But then it goes back to concave up. Now, I don't know about you, but without that inflection point over there on the right, all I see is like a red line that kind of goes up. Like I could not have seen that. That's what calculus adds to this a little bit. It's actually concave down on the left side of that point, and it's concave up on the right side of that point. I don't know if I could have saw that without calculus alerting me to it. Do you see what I mean? So I purposely made a uber weird graph here just because without calculus, even with Desmos, it's kind of hard to understand what you're looking at. So armed with the first and second derivative, you can analytically understand what a graph looks like, even if it's got some kind of hidden behavior to it. That's what's kind of cool. So this inflection point was really surprising and told me some things I didn't realize. So that's kind of cool.
Could we do this with an easier graph just so
Yeah, don't you
it's
feel
kind
like
of easier to understand?
Don't you feel like kind of like, come on, man, chill out a little bit? Yeah, that's exactly what I want to do next. So let's look at another example, and we're going to run out of time for this one, but let's look at another example that's much nicer, something more, it's still weird, like it's still a graph you've never seen before, but it's not going to be quite so strange. And by the way, we're going to do the same thing Thursday. Like we need a lot more time with this in the saddle, and there's nothing new to teach you Thursday. I'm just going to give you some more examples. So let's consider this function, f of x equals e to the x multiplied by, notice you can't multiply this one out. And I'll make up kind of a parabola in there, and then I'm just going to slide it up 3 so that it gets it off the xy axis a little bit. So this time I could not distribute the x to the 2/3 inside, and so I really have to do the product rule this time. And so in the interest of time and to kind of hustle, let's see if we can get going on this. And so I want to find first derivatives so that I know slopes any place I want, and I want to find second derivatives. And so let's go find these. So the product rule says derivative of e to the x is, well, e to the x. That's kind of surprising. Times the expression itself left alone plus the e to the x left alone, weird that it looks the same, times the derivative of the parabola, which is 2x minus 3. And remember, we love plus signs because now I can do the derivative of 3, which is actually nothing. So again, I've got to set that equal to 0 and solve it. And so if I do that, it would be a lot easier if I factored the e to the x out of both of those, because then I can actually add what's inside together. In other words, what's left inside? X squared minus 3x plus 2 plus 2x minus 3. So I actually get x squared minus 3x plus 2x and then 2 minus 3. Like that's actually my derivative, a way nicer representation of my derivative. Notice I didn't have to do anything crazy algebraically. I didn't have to multiply this by something weird. It's like, this is, I'm pretty much done right here. Now, if you have junk times junk equals 0, because remember, that's where I want to go next. I want to say, when is this equal to 0? Does it make sense that e to the x equals 0? Could give us some answers. When is e to the x equal to 0? Unfortunately, never. Maybe it's fortunately. It's actually never equal to 0. It doesn't matter what x you pick. I'll erase this, but e to the x actually looks like this as a graph. When is that equal to 0? Never. It never hits the x-axis. In order to be equal to 0, it would have to hit that x-axis down there somewhere, and it never touches it. No matter what you pick for x, you never get e to the x equal to 0. So that's, for us, that's actually kind of good news, because it just means, well, good, I guess there's not as many zeros to this graph. But the second one, of course, is going to yield some answers. Like, what about when x squared minus x minus 1 is equal to 0? Notice there's 2 answers to that, if I'm not making this some weird question. There's 2 answers, and so that means, like the last problem, there's 1 maximum and 1 minimum, and so that's kind of cool. Again, in the interest of time, you get this happening at x is approximately, quadratic formula, approximately 1.62. All right, quadratic formula is the kind of thing I'd want to see on a test. Tell me that you did it. And negative 0.62. And just so that it's a little clearer in the notes this time, let's go back and put 1.62 back into the original equation to see the y that goes with it. And when I do that, I get 1.62. When I do that, I get 1.809, or about 1.81. And when I put negative 0.62 back into the original graph, again, to see what y goes with it, I get a y value of 5.28. So now I have values for my maximums and minimums. I have the point 1.62, 1.81, and I also have the point negative 0.62, 5.28. So again, that's huge, like all of this calculus, so that now I know maximums and minimums. So let's get our mind around what the graph of this might look like then. So if I cruise down here, and notice I get some bigger numbers this time, so I don't have to make such a weird looking graph. just going to use the boxes as being worth 1 this time. So 1.62, 1.81, maybe that's about there. And then the other one is negative 0.62. 5, 1, 2, 3, 4, 5.28. So maybe about there, 5.28, somewhere in there. Again, if this problem is not weird, I find myself thinking, kind of like Eve said before, I kind of find myself thinking, you know, the graph probably looks something like this, like a cubed equation. Right? Is that, I mean, a rough guess. Maybe I'll erase that later, but let's go on and find the second derivative now. Let's go find the second derivative and find the inflection points so that we can see where the transition is. And notice I would kind of expect there to be, just so that you're reasoning, if I'm right, wouldn't there be an inflection point like right there somewhere, like that's a transition? So maybe there's only one. Or maybe the graph, you know, levels out over here, which means there's a second one right there. It goes from concave down to concave up. Maybe there's more than one inflection point. Maybe there's 3. This is concave up and then it switches to concave down. Maybe there's actually 3 inflection points. You see the logic of why inflection points are going to help me out with my graph quite a bit? So let's go take a look then at second derivatives of x. Again, I have to take the derivative of a derivative. And so I'd like this as simple as possible. And so that's not terrible. This graph right here wasn't terrible. So my simplification of it, if you will, was useful. That's not good. Duplicate. So there's my first derivative. Let's take a second derivative. So the second derivative then would be, let's go with blue, the derivative of the derivative. Again, I'm looking at that multiplication and thinking, oh, product rule again. The derivative of e to the x, which is e to the x, times the junk left alone, plus the e to the x left alone times the derivative of the parabola, which would look like that. So there's my second derivative. And again, I want to set this equal to 0, so it makes my life really easy if I factor e to the x out, leaving x squared minus x minus 1 plus 2x minus 1. I guess that'd be x squared minus x plus 2x would be plus x. And minus 1 would be minus 2. Like there's my second derivative, which I now can set equal to 0 and find these inflection points. Like last time, the e to the x isn't going to produce any. So e to the x is never equal to 0. So that produced none of them. But x squared plus x minus 2 equal to 0. I'm guessing it'll produce 2, but maybe it produces none. It almost seems impossible to produce none, because how could the graph transition from concave down to concave up without some inflection points? So it feels like it's going to have 2, but notice that's interesting because I thought maybe it has only 1. Well, apparently not. It doesn't have only 1. That's interesting to think about. So what do I get? So this produces 2 answers using the quadratic formula. I get x is approximately, well, actually I get equals. That's kind of cool. I got equals 1 and equals negative 2, which means I could have solved this by factoring. Really? Let's see, x squared, oh yeah, x plus 2x minus 1. So negative 2 and 1, that actually makes sense. And so my inflection points happen at x is 1 and x is negative 2. What y values do I get? Well, I got to go back to the graph to find the y value. When I put 1 in, I get out exactly 3. That's kind of cool. 1, 3. I get a perfect inflection point. That's really weird. That's such a crazy graph. And by the way, I just made this graph up. It's amazing that it came out with a whole number for that. When I put negative 2 in, however, I get 4.62. And so again, huge importance, like in terms of understanding the graph. these inflection points are huge. And so let's go graph them now. Let's get rid of the nonsensical guessing I was doing. All I had were these two maximums and minimums. And now I've got these inflection points. And so let's switch to red. Let's see, 1, 3. 1, 3 is right there. That would make sense. Again, I'm just going to slow down for a second. That would make sense because if this is concave down and then it switches to concave up, wouldn't there be a transition right in there somewhere? That actually makes sense. I'm not surprised to see that. Notice it's not right in the middle. It's not like perfectly in the middle. It's actually closer to the bottom one. That's kind of cool. And then there's a second one though at -2. That's interesting. -2, 4.62. -2, 1, 2, 3, 4.62 be about right there. Do you agree with that? So what must this graph look like then? Well, let's see. I guess it's kind of like I said. It looks something like this. At least that's what I'm thinking right now. But again, what happens outside of that? There's no inflection point over here. So what does that mean that graph must do from there?
Going up.
It's got to go up. It can't do this. Does it make sense? Because then there'd have to be another inflection point right there. It's just continuing to go up. Let's just go up like this and kind of look like a parabola. So again, it's just so important to see that. You see the transition there. But then over on the left side, it says there is an inflection point. So what's going on over there? Does it go like this? Like a cubed equation?
I'm thinking it levels out.
Yeah, it goes to the left. Curve to the
Okay.
left.
Does it make sense that like from here to here, because the inflection point is a change of concavity, but it's actually saying when it gets here, there's a change. And did I just draw a change? No, I just said it kept on going. What I just drew is if there was only one inflection point, that red one isn't there. So this is not what's happening. How would it transition? Well, wouldn't it have to transition to being concave up? Maybe something like that.
Yeah.
You see how the inflection points are kind of cool? They tell me things. How do I know it doesn't turn around and go back up again?
Because then it would have a higher maximum.
And also another inflection point.
Because then it doesn't have another inflection point. What does it
No,
have?
it'd have another maximum minimum critical point.
Yeah, it'd have a maximum or minimum down there. Does that make sense? You see what I'm saying? Like how powerful this is? So this actually must switch concavity, but just level out like this, like almost asymptotic to something.
Is this the e to the x part of our graph?
Exactly. This is
Because
the contribution that e to the x is making, apparently. So it's like e to the x times a parabola. It's like an e to the x times a parabola. So who wins the parabola? Well, notice over in this section, it's got kind of a parabola look to it, but out here, the e to the x kind of manifests itself, if you will. And so, you know, again, it's kind of like, you know, two parents make some different kid. And so you see effects of each one of them inside this graph. And so that's just kind of cool. So as far as leaving you with this, I just want you to notice it's like concave down. That's what you do. That's what you look at inflection points for. But then it actually switches. That's what inflection points do. And now it's concave up and now it's concave up. So it's extremely important to notice, hey, this is a max and that's a minimum. But this is an inflection point and that's an inflection point. I don't know if I would have understood this graph without seeing those. And notice in this case, I don't even need to go look at, I only found 4 ordered pairs, and yet I own a really complicated graph. I mean, that's kind of cool, isn't it? Again, is it obsolete? Yeah, you could argue that. Let's quickly go look at Desmos just to kind of verify that we actually didn't screw this up. Since I already have this sitting in here, all I got to do is go back and make an E in there, right? Except for this was x squared minus 3x plus 2. It's almost the same graph. You can see that I invented these perhaps because I was playing around with the same exact set of equations, trying to come up with something kind of interesting. E raised to the x power. There's a plus 3 on the end of it, though I forgot about the plus 3. So see how it is indeed leveling out on the left over there? And actually what's kind of cool is because of the math, we know that it levels out asymptotically. It can't go back up again, otherwise there'd be a minimum over there, and the math said there isn't one. So it's actually leveling out kind of against, well, it looks like it's leveling out against, well, I guess I can't tell. Yeah, I can. It looks like it's leveling out against 0.6, but you know, is it a hair under 0.6? I don't know, but I got it thanks to calculus. I only found 4 ordered pairs in a ridiculously complicated graph, and yet I completely figured out what the graph looked like just with 4 ordered pairs. You can see how caveman that didn't have calculators or graphing calculators and so forth, like you could actually figure something like this out. It's kind of cool. We're doing it analytically. We're using our brain, not just kind of cheating. As I said, though, there's a really good argument that, like, why even put this in the book anymore? You know, this, I mean, that's an application for derivatives, but we got technology now. So, you know, do we need to know this stuff anymore? I think there's an argument. If you're going to be a teacher, you should have an answer to that question. As I mentioned, I'm going to show you some of the examples I'll show you on Thursday. Since we're not meeting tomorrow, there's some hidden behavior in them, and the calculus is going to sort of tell us to go looking for something. Like, for instance, if the graph was going along level, but there was like a little bump in it, does it make sense a bump would cause a maximum and minimum? So if there was a bump out here somewhere that we can't see very well, does it make sense calculus would have told us that it was out there, and then we could go look at it? Like, that's what's kind of cool. And again, I find that, you know, odd. Like, when's that ever going to happen? It's not a business application. That's never going to happen in any practical context, but it's just kind of cool to realize that calculus not only tells us what we are going to find, but it also tells us that there's nothing out there that's weird. You see what I'm saying? It's not just that we found 2 inflection points. It's that we did not find 3. There's not 3. There's not 4. There's not 5. There's 1. There's a maximum and a minimum. There's not 3. There's not 4. There's not 5. There's 2. So it tells us nothing weird happens out beyond what we can see. So that's kind of cool, I think. So you may remember from Math 111, like, does this go up forever? Calculus says, yep, it has to. And zooming out does not prove that. Does that make sense? I mean, we're up to y is 2000. Does it look like it's continuing like this forever? Well, it looks like it, but how do you know when it gets up to 50,000 it doesn't turn around? Calculus says it doesn't, because if it turned around, there would have been an inflection point. There would have been a maximum, and we knew it. We know it isn't there, and so that's kind of the proofy side of all this. All right. I think that's enough for now. Notice, by the way, just as a side note, going out the door, it crossed at 0.5, which I actually could have, I could never move that. I could have known that. If you go in and put x is 0 into that, you have e to the 0, which is 1. And then you have a 2 in the parentheses and a +3 out there. So it's 2 + 3. Oh yeah, when x is 0, y would be 5. Don't forget, you can still find x-intercepts and y-intercepts. This graph is interesting in that it has no y-intercepts. Y is never 0. There's nothing you could put in for x that ever gives you a y is 0, but you can get x. You can get x is 0. So, you know, those points are somewhat helpful, but not near as helpful as maximums and minimums and inflection points. All right. I want to keep going, but I cannot. Stay after if you want to ask me questions as usual. Otherwise, I'll see you on Thursday. Do something fun tomorrow.
I remember from like pre-calc, concavity is like smiley face is like concave up, frown concave down.
Yeah.
It's kind of hard for me to see it with the flattening out. So just like as a overall, like if I'm ever doubting my inflection point or anything, it's f prime prime of x. If that's positive, it's concave up. If it's negative, it's concave down. Is that like a definite?
That's a definite fact. You can count on that. You can take that to the bank. If you plug
Okay.
in any value for x, you have to plug a value in to see, but if you plug a value into the second derivative for x, you don't even have to know what the number is. If it comes out positive, you know it's concave up there. You plug a value for x, comes out negative, it's concave down there. You know that for sure.
Okay. Later.
Later. Good question.
This doesn't pertain to today, but I kind of want to show you